Hello, Professor Block. Welcome.
Hello, good morning. Thanks. Nice to meet you virtually, and thanks for the invitation.
Yeah, and thank you for preparing this lecture for us.
Yeah, no worries. I'm looking forward to a new audience. It's always great. I hope that there will be some good questions as well.
Yeah. So in this room, there are dozens of audience, and there is another broadcasting platform named Philippe. Maybe you have heard of that.
About it. Yes. Yeah.
Usually there are like 2,000 or 3,000 audience there.
Okay, that's exciting. Yeah.
And they may like type in Chinese questions, and I can
You will
translate
then
for you. Yeah.
Okay. Perfect. That sounds good. Yeah.
Are you in Zurich now?
Yes, I'm in Zurich. Yeah. We're recommended not to travel too much and to work from home. So it's interesting times.
Yes, yeah, everywhere.
But I see Lutger is at ETH. Right? Lutger?
Yes, but it's very rare. Normally I stay in Vienna. I'm here for 2 days every 2 weeks.
Thanks also to you, Lutger, for the invitation.
Yeah, pleasure to see you. Looking forward to have your talk. It's a very long time. I heard you last time.
Oh, wow. Okay, so the pressure is on. Yes, of course.
Yeah.
So you two also haven't meet for some time. Yeah.
Oh yeah, quite a while. I mean, in general, maybe we don't overlap always, although we see each other quite a bit in the building when Lutger is there. And but we have all somehow mainly worked from home since mid-March, so that's for sure a while ago.
Yeah. Maybe next year you can come to Southeast University.
Well, nice. Yeah, sounds like a plan. Yeah.
So I will first briefly introduce you in English and Chinese, maybe in 3 or 4 minutes. Then we start. Yeah.
Great.
Again, thank Professor Block for sharing his lecture today. And thank all for coming to this webinar. This event is hosted by ETH Zurich and Southeastern University. Philippe Block is professor of Swiss Federal Institute of Technology in Zurich. He directs the Block Research Group together with Dr. Tom van Miller. Philippe is also director of the Swiss National Center of Competence in Research in Digital Fabrication. He studied architecture and structural engineering at VUB in Belgium and MIT in the US. Following the model, strength through geometry, his team applies research into practice on the design and engineering of novel shell structures. 欢迎大家来到多南大学建筑学院的在线论坛。本次活动是由苏黎世联邦理工学院以及东南大学一起举办的。Block 是 ETH 这苏黎世联邦理工学院建筑系教授，同时担任瑞士国家研究能力中心负责数字建造。那么Block 教授在布鲁塞尔自由大学以及 MIT 攻读建筑以及结构工程学。那么他的研究重点是曲面结构的设计、优化以及建造，特别是无配筋的砖石拱顶以及混凝土壳。那么他最著名的作品应该是06年威尼斯双年展的壳体结构。那么他用的石材非常薄，只有5到8厘米，那么但是跨度呢达到了10几米。那么其中应用了先进的结构优化以及数控加工技术。那么我们经常说建筑跟土木是一家，那么 Block 教授在这方面做了大胆而前卫的尝试。那么他是图解静力学专家，研发了多种力学模型， 基于犀牛开发的设计工具，像 RenoVault 已经在全世界得到了广泛的应用。同时，他的团队还在基于 Python 语言，开发建筑跟结构设计的软件框架，就叫 Compass。因此 ，Block 教授在科研跟实践两端都做了开创性的探索。因此，今天我也非常期待他的讲座。Block Research Group develops computational structural design using digital fabrication. Their research pushes construction innovation to address the grand challenges posed by climate change. Today, we are honored to have Professor Block here in our webinar. He will give us a presentation titled Strengths Through Geometry. Professor Block, you can start your speech. Yeah. Thank you.
All right. Thanks a lot for the introduction. Thanks a lot for the invitation. I'm very excited to be able to share my our research with you today. And I will indeed start with the motto that we follow in our group, so strength through geometry. All right, so let's get going. I like to start my lecture by first frame why we do what we do. And so you already heard about climate change and the environmental pressures that our industry is causing. And for me, the reason why this is really something that we cannot ignore is because there is this estimate that in the next 30 years, there will be a 20%, there is an expected 20% increase of world population, which translates to more than 2.1 billion more people to be expected on this same planet. This has a direct relation to construction because another way to look at that, and these are rough numbers, but in order to provide dwelling and infrastructure, so housing and infrastructure for all these people, we need to roughly double the existing building stock. So everything that has been built until now, we need to roughly double in order to provide adequate solutions. Bill and Melinda Gates in 2019 in their annual letter translated it to this to really clarify what that means. If we need to provide indeed this doubling of the building stock, that means that we need to, on average, build the equivalent of one New York City every month for the next 40 years. So this kind of gives you maybe already a sense of how much construction needs to happen. I hope that you're aware, and if not, that is why I include these couple of minutes as introduction, that this comes with huge amounts of challenges. We are, as an industry, already responsible for quite a lot of, I think everyone should mute their mic, a lot of pollution. We use natural virgin resources quite irresponsibly. And then last but not least, there is our industry also generates quite a lot of waste. So not only during construction, but also in demolition and so on. Can I maybe ask that everyone puts on their mute button? Or can the host mute everyone except for me? Apologies. Sorry, can this be solved, please? The mute button. Okay, anyway, I'll continue, but this is extremely, so DMOM Demon, whoever Demon is, can you please mute your mic? Demon. Thank you. All right. So and then something that I will be talking about less is that our industry also is a major energy user, but that is, in my opinion, less important. But just to summarize this impact of the build and construction industry, again, these are very rough numbers. You could argue, is it 35? Is it 39? Is it 40? Is it 42? But this is easy to remember. We are responsible for 40% of human caused emissions, so that relates to pollution. We extract a huge amount of natural resources. We cause, again, and these are all global numbers, a lot of excess, which is the waste, and then energy as well. So with these few kind of initial statements, I hope that you agree with me that we do need to rethink how we design our structures, but also how we build our structures. And as a structural designer, I particularly feel responsible to try to act and to react to this. And particularly because this is, for example, a very typical distribution of weight that you would have in a multi-story building. So if you build a building of 10 floors or higher, then this is a very common image. And what are we seeing here? 75% of the building is actually in the structure. So you have this really weird situation that the structure is actually mainly there to keep itself up. So the imposed loads, only a fraction of those are actually the occupants. So this to me really shocked me and made me realize that we, as a structural designer, one can really have a lot of influence in this irresponsible use of materials. One has two kind of emissions. The one are related to the blue one are the embodied emissions, which are somehow constant. That is kind of what is related to the construction, what is related to the building materials used in a construction. And then the orange one is the operational energy. But they are very easily, one could argue, and I'm showing this here on the right, that with greener sources of energy, you can very simply reduce this. But what to do with actually everything needed to construct your building? There, and this will be the only somehow equation that I will be showing, is it's actually quite simple. You have two things you can work on. Either you can significantly reduce the structural mass, so the quantities of volume so the volume of structure used, or you can, and that's the ECC, you can reduce the impact of that specific material. And so I will show strategies how we use strength through geometry, but also something which we coined as material effectiveness to address these things. So do notice that material effectiveness is not entirely the same as material efficiency. And so we will see why that is important. And then, as introduced, we use computational design and digital fabrication as opportunities to basically bring these potential innovations to market. So my group is now exactly 11 years old, and in the first decade, roughly, we did a lot of prototypes, we did a lot of exhibitions, we had the opportunity to work with some star architects to have this kind of visibility. This was extremely important, and I also want to, at this point, maybe make a point that I believe that these kind of demonstrations are very important to actually start a dialogue with your colleagues, but also with people from industry. But all of this is really not enough. And so now we are trying to get to that next step and to make things really happen. So I'm looking forward to the next decade of hopefully impact and not just appearing in magazines. So first, before I go to the main point of strength through geometry, let's maybe, I want to kind of tease a little bit with a few things that we are doing by combining computational design and digital fabrication. And for that, I will also show maybe a shell structure. So here, maybe a first hint that double curvature is really good. This is a Pringle, so a chips, carrying 500 times its self-weight in quite a bad loading case. So this maybe already shows you that geometry can really help us to create a robust or stable structure. But we don't see too many beautiful surface structures, for example, in concrete, only for unique projects like the Rolex Center in Lausanne here. And this is only for unique projects because they need a unique budget. And this unique budget goes to providing of a full foundation, all the scaffolding, then often months, if not years, in fact, of milling and fabrication of a formwork that will turn into waste after only 28 days. So we wanted to challenge this kind of process by reintroducing or by introducing or further developing flexible formworks or super lightweight formwork that takes out much of these inefficiencies. So this is a hybrid cable net and fabric formwork. And in a nutshell, this slide maybe nicely summarize what we're after. So on the left, you see the status quo, where basically through brute force, a fully rigid formwork, you kind of keep you keep the geometry where it needs to be. And then you see indeed that the foundation, the logistics, and also the cost of scaffolding, but then most importantly, the formwork strategies that are almost standard one-offs. And on the right, you see what this could offer. So you can significantly reduce boundary conditions, so foundations, but also you can practically take all waste and material out. You could even design it such to be reusable. I will talk about this later. But also you see that the space below can be already used so that the next stages in construction can happen. One thing that has to be said is that nothing comes for free. So if you want to have these efficiencies, then you need to design also a formwork that follows the logics of how to generate a stiff formwork. So it means that you cannot just have an uninformed design and then try to make it with an efficient formwork. No, you need to fully embed into your design process. You need to embed the limitations, but in my opinion, also the opportunities of such formworks. So the idea is to use something so lightweight to build a concrete shell. So this was the cable net of a prototype we just we finished in 2017 for a project that is now on site. And you maybe already see how lightweight this system is. So for a concrete shell of more than 20 tons, we will be using a formwork of only 800 kilograms. So here you see 500 kilograms of cable net. We designed it such that it came together like a kit of parts by a very small team of 3 people in just 1 week's time. And again, this might sound a lot, but compared to literally the months of preparation, of milling, also the assembly, the complexity on site, I would argue to realize this non-standard geometry with this kit of parts is quite an easy task. Then after this cable net is assembled, the fabric comes on top. We had to, of course, develop some algorithms to correlate the pre-stressing of the cable net to get it exactly where it needs to be, because the system here is actually pre-stressed such so that under the weight of the concrete, it settles and it hits exactly the perfect geometry. So this image maybe gives you a little bit of sense of the scale. This was a shell of 10 meters width by 20 meters and then 7.5 meters high. So almost 180 square meters of concrete surface. And this was done on this fully flexible, reusable formwork system. We developed and this is a huge opportunity, is that now that we are rethinking this forming, we also rethought how to do all the sequences on site. So for example, the nodes were designed such that they also became on the same axis of the node. We had the space holders to basically define the local thicknesses of the concrete, but also, as you see here, to attach the reinforcement. For the prototype, we used carbon fiber mats, a very efficient kind of strategy because it allowed us to reduce the thickness to the shell to only what structurally is needed. but also to only use one layer, which would be much more complicated with typical reinforcement. So here you see then the concrete being applied, and this was a nice success in 2017, this prototype. So again, we are talking about 20 meters by 10 meters by 7.5 meters, so quite a large surface, and the thickness goes from 3 centimeters at the edges to 8 centimeters at the support. Something that maybe you notice here is that this is of course not the famous Swiss architectural fair-faced concrete. So there is some imperfections in the concrete, but because we did the entire process with our industry partners, they knew exactly what happened where, and they were the ones that actually gave the client the full kind of confidence to go forward, because they signed, they promised that the next one would be perfect indeed. So this is something that maybe shows already that if you can really rethink the entire process and the links between engineering, fabrication, and then execution, that you can start to reintroduce these efficient structural forms at a realistic cost, and more importantly, also time frame. Another project where we pushed the boundaries maybe a little bit further is where we started to use 3D knitting. So the knitting of technical textiles and to use those as a super lightweight fabric formwork. This is the work of one of our postdocs, Mariana Popescu. You see her here in front of one of these knitting machines. So this is a standard knitting machine, which is used to make sweaters, to make any type of garment. And we kind of adapted the things that we do with it in order to generate these formworks. So again, this is how it looks. So it has these 2 beds. And then for this project, arguably, we built the largest scarf in the world. So here you see this knit being laid out. But what was interesting is that we then vacuum packed it, and it could be brought on site just-in-time delivery in just 2 suitcases. So what's interesting about this knit is that in this knit, we basically embed all the non-standard components. So it is this 3D knitted textile that gives you all the relevant references and kind of non-standard pieces that on site no longer have to be assembled or placed in the right place. It can just be taut, it can just be tensioned into place. Then together with our colleagues in civil engineering, this is Lex, they developed an extremely cheap, fast-setting cement-like paste that allowed to basically freeze this geometry, so stiffen this knit so that together with its good double curvature, but also with this very small coat, that it becomes like a standard formwork. And maybe you notice here already these little bubbles. These bubbles were inserted. These are little balloons that are controlled and constrained by the knit geometry to actually, in the final shell, generate these ribs in the 2 directions, right? So these become pockets into the rib. And so this allows us basically to generate a very sophisticated shape with such a simple technique. What I thought was exciting about this project, which we did with Zurich Architects in Mexico City, is that I knew from experience from other projects that Mexican crafts are on an extremely high level. So they have the habit to do high standard concrete finishes. And so what we achieved here, I think, is an efficient or the right insertion of digital or innovation of digital fabrication. So rather than going on site and taking everything over and ignoring the local kind of opportunities by bringing in robotic kind of whatever, we actually just provided a better canvas for the local workers to do what they do extremely well. And that is something that I really enjoyed in this project, this exchange over multiple continents and building upon each other's strength indeed. So this was then the result. It was still a pavilion indeed, but nonetheless of roughly 6 by 6 by 4.5 meters, so a large surface of concrete, so more than 50 square meters of concrete. So this shell weighed about 5 tons. In this project, we, unlike the shell that we showed earlier, where we took the formwork down, here we wanted to try to explore another materiality for concrete. So we kept the knit as an exposed, different kind of finish on the inside of the geometry. But here from the top again, you see how thin this shell is. And this thinness was possible because we had these ribs running in two directions on the inside, created by the cavities in this two-sided technical textile. But now what is maybe key and why I spend a little bit more time presenting this project is because I think the numbers might surprise you. The entire formwork, except for the external frame, which could also be a reused or rented kind of scaffold. So what am I talking about? The cable net inside. So we again have a cable net that provides the main stability. And then the knits and all the components related to this cost in total only $2,500 US dollars. That also, by the way, includes the stiffening paste that we put on top. So this is for such a sophisticated piece, this is not a bad kind of starting point. Perhaps this is also a big advantage that indeed we could bring the entire formwork on site because it weighed only 25 kilograms. But then here, this is maybe an important point that I already emphasized earlier, is that to generate an equivalent surface, we would be milling about 750 hours, while the fully knitted kind of formwork could be produced in only 36 hours on this knitting machine. So why is this important? 750 hours means that we would be milling for 3 months non-stop in order to provide this formwork. And this doesn't even include assembly, logistics, and all the challenges that you would encounter on site to assemble such a formwork. And this is maybe an interesting detail that from the very first email from Zurich Architects inviting us to collaborate on this to the opening of the exhibition, there was only 3.5 months. So this maybe gives you a hint that such a fully engaged computational process that really takes structures, fabrication, construction consideration in the design development, and that we could rethink the entire sequence, but also length of phases. Next, and unfortunately because of COVID, this project has been extended, is that I was hoping to be able to show you a project where we also address this. These non-standard geometries, it's in concrete, it's not just about shaping them, but it's also about the reinforcement become a really big challenge. And so in the next demonstrations and research, we are starting to integrate these reinforcements directly in this same lightweight knit, so that this lightweight package comes on site, not just as a forming piece, but also as a fully integrated reinforcement. This is being done in the NCCR digital fabrication indeed, together with colleagues in concrete and concrete mechanics indeed. But in the bigger picture, what I see as a relevance, what is even cheaper, what is even easier than sending 25 kilograms is just sending data. And these kind of knitting machines are readily available all over the world. And so you could imagine that these become also distributed fabrication factories that can locally provide these kind of supports. So I don't know if you've seen the lecture of Fabio Gramazio and or Benjamin yet, but if you have or if you will, they surely talked about the DFAB house on the Nest platform at EMPA in Dübendorf in Switzerland. But we are building another demonstrator here on the more prominent corner. And it might look something like that, but the key thing that I want to say there is that the roof will actually be a demonstration of what I showed earlier. So this flexible formwork, that is why we did this prototype in 2017. But now we have a little bit more of a challenge that we built on top of a building, which is, I have to admit, not ideal. It's also not an ideal demonstration of what we want to show here, but this project gave us that opportunity. because of mainly building systems and building physics kind of so insulating kind of reasons, we will be building a 2-layer shell of twice 3 centimeters. So this is actually an outdated geometry. Let me maybe highlight, you see this axis here. So this axis comes from the nodes of your cable net, and they directly allow to very simply add the shear connectors. They give you all the thicknesses. They allow a very efficient clamping and fixing of the reinforcements. They also give us then basically all the way to providing the waterproofing and then the solar facades panels on top and so on. What I want to re-emphasize here is that we really use these digitally fabricated nodes as the logistical device to make this crazy geometry suddenly become quite straightforward because it's basically 40 by 40 centimeter quite simple patches. A lot of additional testing had to be done. And then obviously, because this is a real project, we need also to deal with all these details that you can ignore in an academic prototype. Details like, for example, the channel where the concrete, because we want to have exposed concrete, visible concrete from the inside flowing to the outside. This is, for example, the detail where the glass facade will disappear in that concrete facade, and to not have a thermal bridge. So to basically make sure that also from a building physics standpoint, everything works. The client asked us to guarantee that we can build within 0.5 centimeter so of tolerances, which you probably know for concrete is absolutely absurd. But so here we are doing some prototypes demonstrating how precise we can build indeed. And then I look forward to see also the expression of the imprint of this fabric into this concrete. Here, this is a snapshot of just before the winter break. Look, I want to point out maybe the cleanliness. So look how clean, how simple the building site is. This is not only because it's Switzerland, but also because the system is really designed to come to be put into place very simply with a small team. As I said, we needed to develop some algorithms to kind of readjust this flexible formwork so that it's exactly where it needs to be. And so here you see this team assemble the fabric. Another reality of trying to really introduce such disruptive kind of ideas into a quite conservative building industry is that you need to do a lot of things yourself. So this is actually my own team, is the Block Research Group, assembling this formwork. So we're not only computational, but I guess also now non-standard formwork experts. So here you see just before closing, and then for us exciting, 3 weeks ago, they started with the spraying of the first layer, which is now finished. And so you here see that the very first thin surface layer has a little bit of fiber reinforcement in there in order to prevent any cracks indeed. So here now we are with the first layer done. You see all these little bits sticking out. That is where then very efficiently the shear connectors will be connected on the insulation blocks, and so on and so on. So in a way, this very crazy geometry is being delivered. Everyone here on the Swiss side seems to be surprised how smooth this process is working indeed. But as I already kept emphasizing, none of this comes for free. So all of this needs to be pre-planned, needs to be kind of simulated and kind of designed from scratch. And that is why we have in the last 5 years been developing this open source framework, Python-based framework, Compass, to allow to collaborate, but also to exchange kind of knowledge and solutions with other people. Mainly with research institutions. So this Compass allowed basically this is not something like BIM, but it's really a centralized, lightweight handling of geometry and attributes and information to then generate all the relevant information for our partners, many of which in this process have barely any digital competence. And so we are doing this, we're really challenging these approaches in a context where we are not working with specialty contractors, but really with very standard, more conservative partners. And indeed, when you do start from this kind of geometry kernel where everything is matched, you have no hesitation, there is no hindrance to kind of also embed on the top level these new algorithms that we had to develop to generate non-uniform pre-stress values, to then take this geometry directly and automatically run the engineering analysis, check the fabrication constraints on the bottom left, or even steer the total stations to kind of do this, this measuring for the control systems to retighten and loosen kind of the geometry. So this for us was a nice kind of a demonstration of rethinking the typical sequential design and execution process to have a more integrated, holistic kind of approach. Okay, but the key message for me is indeed strength through geometry and material effectiveness. So for me, all of this kind of fascination or insight started during my PhD at MIT, where I actually developed a new method to understand the safety and the stability of historic structures in unreinforced masonry, in brick, in stone, and so on. As, for example, these beautiful fan vaults at King's College at University of Cambridge. So they're standing for centuries, they're standing without reinforcements, so just because of their good form. And for example, this shell is proportionally, literally as thin as an eggshell. If you were to cut an egg in half and you measure the thickness of the egg over that span, this is how thin these unreinforced structures are. So in the beginning of the BRG, we started to develop computational tools that, like RhinoVault, that allow designers to explore these kind of forms, but explore them while understanding their equilibrium. But as you know, you can do whatever you want on the computer. So you can simulate or suggest anything. So that is why we took the 2016 Venice Biennale to try to clarify what this really means, to shake our colleagues, to shake the community, that what you can achieve when you get the geometry right. So what you're looking at here are 399 cut pieces of limestone that are held together by equilibrium. There is no reinforcement, there is no mortar, there is no glue. These are just cut pieces of stone. And this is possible because the geometry is fully in compression under all of its loading cases. So we have a very thin shell of an average thickness of 4.5 to 5 centimeters. Only locally to the supports, we increase a little bit. And here to just show some details of the assembly, this is just dry assembled. So this is really no trick. These are 24 tons of stone that are kept in space because they have a good geometry, a structural geometry in equilibrium. So we took an opportunity also this shell was optimized for fabrication. That is why it looks so specific. It is flat on the inside and it has this very efficient carving on the inside. Of course, this is not the very first thing that we do. We had done many prototypes before. This was actually a funny day in 2011. One of the first things we ever built, an unreinforced shell, a tile vaulted shell. And here you see that double curvature gives you really a lot of robustness. And indeed, that was inspired by a historical technique. Maybe you know these beautiful vaults. This is at Grand Central Terminal, the main train station in New York City. This is the Oyster Bar. And these style vaults, so what you're looking at is not just decoration, it's actually one of 3 layers of unreinforced tiles that are laid in a specific technique, but they're laid without any formwork. So they're built basically in space, starting from stable boundary conditions with a fast-setting mortar and a lightweight tile. And that was actually a perfect premise to bring these kind of techniques back for context where material is expensive or scarce and where labor is still plentiful available. And this was then, I was happy to be involved in this project that was finished in 2008 during my PhD. The architect is Peter Rich, and John Oxendorf did the structural design, but Michael Ramage from Cambridge really did most of the planning, construction, and execution. This is a very remote location in Mapungubwe in South Africa. It is a museum where basically this traditional technique was introduced and done only with local resources. So here you see local farmers and carpenters that were introduced into this technique. And even these very large scale structures were done again by these local laborers, just under minor supervision with also local material. So here you maybe see why this is such an efficient technique. The timber you see on the inside, by the way, is a reusable guide. It's not a formwork that you build on top. You don't touch this, but it actually basically guides where the geometry needs to be. Very important, of course, when you literally build with unskilled labor. So the white is this faceting mortar, and then you build up additional structural layers. But the reason that I'm showing you this old project is because of this image, or these two images. On the right, you see that tiles are being carried in very small packages. And that is because this is actually a picture of week 2. First week was a total disaster, and I'll tell you why. The tiles are designed to only take 2 megapascals in compression. 2 megapascals in compression is 10 to 15 times less than a standard concrete being used. So it has barely any compressive strength, but what is very scary about this structural material is that if you take one of these tiles in your hand, you can just break it in front of you. So it has no bending capacity whatsoever. And that is why these happy women are carrying the tiles on site in week 2, because the men in the first week could not be bothered, and more than half of the tiles arrived broken on site, which obviously was an issue. Why am I emphasizing this weakness through this small anecdote so strongly is the image on the left. This is actually the floor, the permanent floor of this museum. And you see these same tiles, if you place them where the forces want to go in compression, become very safe and robust structural materials. So this, to me, was an eye-opening experience, and also an extremely important lesson, that geometry is so important that you can start to really use local, very low strength materials. And an important aspect about this is that these tiles are made just by compressing soil with a little bit of cement. So I think roughly 7% of cement to stabilize those tiles. And that's it. So you actually use the local soil, there's no transport needed, and only a very small percent of imported materials. This works because an arch is a very good geometry for a certain loading case. But if you don't have double curvature, like we had in the Armadillo vault, the stone vault that I showed you at the Venice Biennale, then you need something else to take live loads. So for example, if you have a big point load and the red line represent where the forces would want to travel to the supports in compression. So here you see with this additional point load, you cannot find a solution within this very thin arch anymore. So this thin arch would immediately become unstable, and to say it very simply, it would collapse. So another strategy then to activate double curvature is to locally add stiffeners. And so you see basically what these diaphragm walls kind of do. They provide an additional structural depth, so an additional kind of opportunity for load paths in compression to safely travel to the supports. If you now add a tension tie to resolve the horizontal pushing, the horizontal thrusting of this arch on its neighbors, what we've just done in the last 15 seconds, so I hope you understood all these steps. So in these last 15 seconds, we just developed a 70% lighter equivalent of a floor plate. You see, basically, a reinforced concrete floor plate would need to have a cover to cover the reinforcement for fire and corrosion and so on. But you see that so much material absolutely would not be needed. And this just by reintroducing a common sense, a system that was very well known and used all the time historically, but that we have somehow forgotten in our design vocabulary. So here, this was already successfully implemented in this Mapungubwe project. And you see that in this case, the tension ties also serve as lighting fixtures. And of course, this was done in a context where we try to challenge this, right? Where low-cost housing cannot really be for low cost, because they're trying to build like we do in our inappropriate concrete ways. And in the process, they waste a lot of material. It's expensive because a lot of material needs to be imported. And also what I started with, the pollution of such construction needs to somehow be addressed. At a certain point, I was challenged by my colleagues at ITA that, okay, good that you work in Africa, fun that you do these kind of crazy things with big architects, but what's the real value? What is the real purpose? What is the real opportunity of your research? And that is where suddenly we realized indeed that why introducing this kind of vernacular forms in a developing world context, actually we also have a problem in our context. And the problem is more specifically all this construction, all these floors that we need to build all over the world. Because if I come back to this pie chart here that I showed you earlier, that for medium high rise, so even 10-story buildings is not that high, so 10 to 40, 50 maybe story buildings. This is again a very typical image that 75% of the weight is in the structure. We can refine this even and notice that of these 75%, more than half of that is in the floors. So towards the total contribution of the weight of the building, 40% is in spanning space, is in the floors. So this is actually really a very significant bottleneck in efficiency, and also hence a very significant contributor to pollution, resource depletion, and all the things that I talked about. And this is where I want to step back and try to clarify actually the difference between material efficiency and material effectiveness. So you must know the worldwide kind of agreement on how bad concrete is. This was one of the voted best articles of 2019 in The Guardian that basically described at length that concrete is the most destructive material on Earth. That is absolutely correct how concrete is being used right now. It is basically being used in a way that it doesn't want to be used. A concrete is like an artificial stone. It wants to be kept in compression. It doesn't want to be a beam that needs to bend. That is exactly where everything goes wrong. And you see this actually, if you, for example, look at the embodied energy per unit mass, you see that concrete on the bottom there, and this is a logarithmic scale, by the way, outperforms all the typical building materials that we have. Again, I told you that maybe energy is not the key criteria, but emissions is, so the associated equivalent carbon oxide, CO2 emissions. And there you see that actually concrete again does quite well. So basically what I'm trying to say here is that it's not just necessarily about lightness, but I believe that you will hit those efficiencies when you use all materials how they want to be used. So for example, if we want to use concrete, we want to use it in compression. So we want to use it with a much less volume that we do. And I already gave you a hint at how we can do this. Just by going from bending to the tight arch, we save more than 70% of material on the concrete side. So that means that we're placing concrete only where it needs to be. And so relating back then to their emissions, if we were to use concrete how it wants to, I would argue it is probably one of the most sustainable strategies, because it's a material that we know that can be produced relatively locally and also at the large scale of the construction that we imagine. Of course, nothing will ever beat sustainably sourced timber, but all calculations hint that if we would replace all constructions, which by the way for infrastructure is not possible, in timber, that we have just not enough forests available to do this in a sustainable way. So we need many solutions. And I just wanted to, in this small side note, clarify that I also believe that the world needs to have a much more nuanced and much more smarter discussion on sustainability, and really understand what are really the bottlenecks. And so my point here is that concrete is not necessarily the evil if we start to use it how it wants to be used. And that is then what we started to demonstrate in our 3D floor plates. So this was something that we developed already many years ago, a 5 by 5 meter floor where you only need 2 centimeters of unreinforced concrete because you externalize the tension ties very much like the tight arch that I talked about before. This we also showed at the 2016 Venice Biennale. And this is actually a very nice kind of provocative prototype because this prototype here uses the same concept, but is fully sand 3D printed. So it's using an equally weak material as what we used in South Africa, 2 megapascals in compression. I don't know why all these weak materials seem to end up being around 2 megapascals. But if you hold it in your hand, it breaks in bending. So what we are doing here is we're doing the recommended American Concrete Institute's recommended protocol to apply all the loading cases needed. And we just demonstrated that this very weak material can actually be a fully safe structural floor indeed. If this image doesn't convince you, maybe 1.2 tons of ETH nerds standing on a 2 centimeter unreinforced floor plate with a material properties equivalent to cold dark chocolate, this might maybe convince you. When I started with this research 5-6 years ago, when I presented these results for the first time, then engineers were extremely skeptical and they said this is very academic and so on. But then I confront them with, again, this same project, because if we go back to the oyster bar, these beautiful vaults are built with equally weak materials. They're just simple tiles. They're unreinforced, and the thickness to span ratio, so they have 20+ meter spans. The thickness to span ratios is similar to what we're doing here. So we're not doing anything new. We're basically reintroducing these kind of systems, but we are reintroducing them in a time where we really need to act with respect to the climatic crises and pressures, but also where we now have digital fabrication opportunities that allow us to scale this at real construction scale. So if you think that this is crazy or this is irresponsible, then we should warn the millions of New Yorkers that go to work every single day. Because something that I didn't tell you about these vaults is that these unreinforced masonry vaults are carrying the Vanderbilt Hall on top, which is one of the 2 main entrances of the train station, the main train station in New York. So this is something else that I find absolutely mind-blowing, also sometimes a little bit frustrating, that these kind of structures that work so well, that have been standing for centuries, that they don't appear in our current building codes, that almost no engineers know what to do with this or to analyze them to safely sign off of these, and that we basically have to fight to reintroduce these kind of ideas. So this is something that with my group, we do a lot of work to kind of provide tools to safely design and engineer these systems indeed. And again, considering that more than at least 40% of the weight of these buildings is in the floor plates, there is a lot of benefits to be gotten. And also here, this is an even earlier prototype that we then broke until after testing. And you see also that these cavities can be activated to also start to think about more clever way, rather than layering all these systems to literally avoid any clashes, to start to actually be much more responsible also with the floor heights, and by that offering our clients at least 25% additional real estate in the same total building height, for example. For those of you who build, you might immediately think, what about acoustics? Super lightweight floors are problematic. And this is where, again, I might have some really good news for you, because what's super exciting here is that we are using structural stiffness rather than adding mass. The typical brute force strategy in architecture to avoid contact noises or to avoid the transmission of low frequency, the problematic kind of frequencies through lightweight structures, is actually to add mass. So lightweight steel and timber buildings need to add mass add concrete typically in order to resolve the acoustical problem, while here we don't have to do this because we activate the structural stiffness. This is something very exciting. We are in early development here, but we have demonstrated already that these floors that are so lightweight can have a reduction of 30 decibels on these kind of problematic low frequencies. On top of that, and I don't want to impose this as a style, I am not interested in that. You can hide these beautiful floors, but I also enjoy that these floors become also a very exciting, beautiful geometry if you want to express it indeed. So in summary, the floor elements that we developed are 70% lighter. They have only 1/6 of the embodied carbon, and the reason for this is because 70% would be 1/3 lighter, but that is because they are made from recycled content. In fact, we are using 100% recycled aggregates, so basically from building rubble, and 50% recycled cement. That doesn't mean I'm not talking about adding fly ash and all the typical kind of tricks that are being done to reduce the clinker cement. It's really reusing used concrete construction and extracting the cement to embed it in this new concrete indeed. So that allows us at the current state of development, and we have many ideas with our colleagues in material science to go much better even than that. But at the current development, we are 1/6 of the embodied carbon emissions. And then also not unimportant is that is also the reason that we can go so thin. We don't have to cover our reinforcements. There's no embedding of reinforcements. So we separate compression and tension entirely. And that makes it very easy for long-term maintenance, and at the end of life to just very simply recycle these kind of components. So just to bring this point home, and the reason why we're pushing this project the most, or this research the most of all our researchers currently, is this simple calculation. So let's look at one of these typical medium high-rise buildings. So 25 stories, very simple plan, very traditional core building, and so on. So if we look at the floors, you have a flat slab on the left. That is the current code-regulated kind of solution. The 80% is by adding post-tensioning, right, which is not done all over the world. The 50% is the high-low floors. We're actually building a first version of this in the same kind of unit that I showed where we had the big kind of roof. But then there we had to still make some compromises because it's the very first unreinforced concrete funicular shell floor in the world. So that is why we had to kind of come with an agreement with a local engineer of record. And so not all efficiencies are in there yet. So then the last one, the Rippmann floor system, the RFS, that is the one where we really will hit the 70%. So on the total volume of concrete in the building, this causes a reduction of 35%. What does 35% mean? So again, we are talking just about one building of 25 stories high. That means a reduction of 7,500 cubic meters of concrete. If that again is very abstract, that means, and of course that means that for this building we would need 1,208 concrete trucks less, right? So this is a significant amount. That is how much less material in this one building. But then this is actually an additional key advantage, is that, and look, the high-low floors, again, not optimized, we already reduce the amount of steel by 90%, right? 90%. And so that means that per floor, we can take out 20 kilometers of reinforcement steel. And then coming back to the chart here on the different impacts of different materials. So we are significantly reducing the concrete where it needs to be. So it becomes actually a totally sustainable material. And then the much more polluting material, the steel, we only place where it needs to be. So actually, both aspects cause, I said about 1/6 earlier, the 1/6 is only considering the concrete benefits. Now we are at 1/12 of the embodied emissions. So we have a fraction of the emissions because we only use steel where it really needs to be. So again, this is just for one building, and we need many of these buildings all over the world. But there is another reality that these buildings, some of them, many of them will still be in China, but most of them will have to be in places like India, in the entire continent of Africa. And that is where I am super excited that we started collaborations and we are setting a spin-off company, for example, in India with developers to commercialize this floor in India. And we also are working with the government of South Africa to implement this in new government provided housing solutions. So for me, these are the targets. It's relevant. Good structural form is a good strategy all over the world. But of course, we want to target these markets where still the biggest difference can be made. That also leads me, you talked about RhinoVault. This is actually a special day because exactly yesterday at 7 o'clock, we released the first version of RhinoVault 2, which is an open source framework which goes beyond a plugin that is compatible with Rhino 6, Rhino 7, but also Blender, also in the browser, and so on and so on, because it's really an extension, it's a wrapping, it's a UI provided for all kinds of packages that are based on the open source framework Compass. So if you install RhinoVault 2, which I hope all of you will do after this lecture, then you basically get a mini version of Compass with the installation. That also means that you can start to take your geometries to build additional geometry on that. And this we tested last week in an international workshop. And so also online, you will find all the documentation on how to use this tool, but also how to use this tool to, for example, do some of these projects, like the Armadillo Vault, where you can do the floor, this 3D printed still world record, a Guinness World Record, largest 3D printed sculpture that was done in Beijing. And then on the bottom right, you see a project by Philippe that used RhinoVault to make this spectacular curling kind of shell, or on the top right, a beautiful project in India by Sami Padora and architects, also done with RhinoVault. So all of these projects now, all the way to their materialization, we basically want the world to know how to do this. So we share all our methods through Compass. And so if any of this is interesting to you, then you will find all the tools, all the strategies, all the algorithms to realize or to replicate what we're doing here indeed. So maybe this slide just as a little bit of a call, because I find it super important that we start to share, that we are much more inclusive, open source as an entire industry, because we're all facing the same challenges. Why is everyone reinventing the wheel? Why is everyone wasting time while we have these true pressures of the planet, and these pressures are caused significantly by our industry indeed. So I call for action, and our kind of move to action is to develop these open source platforms for exchange, like Compass, by sharing things like RhinoVault, but also by sharing all our teaching material in graphic statics and structural design. So all my teaching material with Josef Schwartz can be found on this platform, Equilibrium. So I share these 3 websites with you indeed. Okay, but so the main message that I wanted to share with you today is that structural geometry, so strength through geometry, allows you to use less material, so to have less volume. Funicular form, so compression only form, not only allows you to have less material, but also to have very low stresses in the material, and so you can use better material. The link here is that higher strength materials are typically more polluting. So if you can really reduce the stresses in your system, then you can activate local materials, recycled materials, or even grown materials. And then last, through computation and digital fabrication, I showed you some hints how we approach basically the shaping of these non-standard efficient structural geometries to produce significantly less waste. So with that, I am also pleased to share with Hao that I spent exactly 1 hour as requested. And so I'd be very happy to take any of your questions. Thank you very much again for the invitation and for joining this lecture.
Thank you. Thank you very much. Professor Bloch showed us the latest advantage in design, engineering, and construction of doubly curved shell structures. and he reveals the methods upon which the unreinforced shell structures are based. And he also shared the latest software, the Compass, Rhino Vault. These tools can offer us better understanding of flows of forces in three-dimensional space. And with these design tools and design strategies, we can reimagine the traditional material like concrete and stone. Now, yeah, we welcome all the questions from Zoom and from the Bilibili platform. Audience from Zoom can directly ask Professor Block, I think.
Should I stop sharing my screen maybe? How? Should I stop sharing?
Yeah.
Yeah, okay, good.
Good.
Should I stop sharing my screen maybe?
So maybe I ask the first question.
Okay, yeah.
So I think it's relatively easy to analyze the balance of static forces. But in the reality, we also consider like wind, like snow, or the buckling of the shells. So I guess there is a big difference between the ideal environment and the real world. Like how you deal with the difference between.
Okay, yeah, that's an important question, because if that's I focus, of course, on the generation and the initial design state. So I didn't show you all the engineering that also obviously needs to happen to realize these kind of structures. But why I actually focus on the design stage, and also why we develop tools like Rhino Vault, is because if you get the initial geometry right, that is already 85 to 90% of the important steps, right? So just getting that first geometry right already solves many things in the long run. And so more specifically, so obviously you need to not only take the self weight, but also live load cases. So people walking on it, wind loads, earthquakes also. So for example, the stone vault in Venice was designed for earthquakes. And there were, in fact, two very small earthquakes during the exhibition. So the shell nicely stood. What I'm saying is that there's different strategies in these shells. The best one actually is to have good positive double curvature, right? So because if you have good double curvature, that is equivalent to increasing the structural depth of your shell. And that means that even though you have a thin geometry, the structural thickness is much, much deeper. So you actually use geometry to give the structure that robustness to take different loading cases. So this you can actually nicely demonstrate when you do the engineering. But so the key message that I would argue there is actually to have good doubly curved, positively doubly curved geometry in compression. If you cannot do this, like in the floor system. So for example, the floor, you said correctly, the floor is not only very shallow, so it cannot create sufficient double curvature, but it could also buckle because it's very, very shallow. And so a lot of force is in the shell, so that it could become unstable through buckling. And that is why we add the stiffeners. So the stiffeners do two things. They basically allow different force paths for your loads to go safely to the support, but they stiffen the shell against buckling. So that is, of course, an important kind of next step is that, but again, I want to emphasize, if you get the geometry right, for example, with the stone vault in Venice, my engineering colleague at ODB, Matt de Jong, he started to do the analysis and he noticed that actually almost any load, this shell was not going to collapse. It was really impressive how many different loading cases you could apply. So he really tested what would make this shell collapse. And so nothing had to be changed. And again, that was because the first step of actually discovering that good doubly curved geometry, that gets you already immediately in the right strategy. So for me, I think that is also missing. How do you even discover these forms? How do you even, in a controlled way, start to explore and understand the relation between geometry and forces and so on and so on? Yeah.
Yeah.
There's a question I see also in the chat.
Yeah.
Yeah, so there is a question about graphic statics, and that indeed graphic statics maybe initially was used to, for example, analyze without needing equations, analyze trusses and simple systems like this. But the question is, can it also be used for design, and how to do that then? And indeed, I think graphic statics can absolutely be used for design, because what is powerful there is that if you now, with our current parametric softwares and things like that, if you set up a graphic statics model and you allow to change the parameters, then at the same time you see what it means for the forces. So rather than doing an uninformed design that then an engineer needs to try to make safe, and then someone else tries to build as cheaply as possible, these kind of considerations are taken immediately from the beginning. And again, there maybe for that question, I very much, so thanks Yushan Han for that. I very much recommend you to check both the Equilibrium website, but also actually in Compass, we have a fully robust background for graphic statics, which is called AGS, Algebraic Graph Statics, that allows you to implement this, for example, in Grasshopper or in however you want to do this. But more importantly, actually, Rhino Vault uses graphic statics to explore 3D equilibrium. So we use the form and the force diagrams. So the designer is actually doing graphic statics to discover three-dimensional equilibrium. That is based on my PhD. So maybe also check that out. So yes, I would say graphic statics is most meaningful for design, because for analysis, we have so many tools, and that is also the problem. Our tools typically say a yes or no. Yes, it will work, or no, it will work. But then what? So, and that is where graphic statics really helps you, because you start to learn the relation between what you're designing and what is then the relation or the effect on the forces. So you start to also receive hints on how to change your design to do better, which is not true when you do a finite element analysis and so on. And I think that is one of the key problems. So thanks for that question indeed.
Yeah, we have now.
Yes, so there is a very important question as well on the chat on bottlenecks in the promotion and the application of such structural engineering practice. Yes, there has been, and there still are a few bottlenecks. A key bottleneck, okay, so bottlenecks on different levels. So first, I think it's about education. I also was not educated during my studies in how to design good structural form. I did both architecture and engineering, and actually in the traditional education, these are not topics that you typically look at. So I think that is maybe where everything kind of starts. But then we also, as I already hinted, we don't have the appropriate codes that actually describe these kind of systems. And the issue with this is that, of course, someone needs to take the risk. And so if you don't have the opportunity to work with good engineers that understand all of this and that are willing to actually think with you and to accept these systems, currently you're stuck because we don't have a code framework that allows to do that. And then the last thing, it's not part of such structural engineering practice, but I would argue that what I've been trying to show is not just also engineering, but a much more integrated approach, because the efficiencies are to be gotten in rethinking everything. So in rethinking architectural design to incorporate all the constraints, but also in rethinking basically how things are built, because these non-standard geometries will never challenge these flat plates that we have been building for literally 150 years. That has been optimized. So from an economical standpoint, it's very hard to only argue for that one component. So we really need to rethink the entire process and get efficiencies in all of that. And so basically these bottlenecks are there. But what I do see as huge opportunities, and you see this already in the UK, in England, in France, in many places in the world, the new regulations that are putting caps and requirements on emissions, on carbon, maximum carbon emissions and so on, these kind of regulations really force the design team to think differently. It is absolutely no longer possible, even within those constraints, to build like we do. And that new climate of actually necessity will hopefully, and I'm actually convinced, will cause actually many new solutions to be introduced, because the status quo will just by regulations no longer be allowed. And so this is a huge, huge opportunity. Another thing that I'm noticing is that clients, maybe currently, this is mainly because of branding, but clients are increasingly aware and requesting much more responsible solutions. And I think the combination of all of that might cause actually an opportunity to give these kind of ideas, like I presented, a boost. In fact, with a very large industry backing, we are currently in a 1 year, so it just started also a couple of days ago, so it's very nice I can give this lecture now. We started a 1.5 year development phase, where we will develop this floor to be a commercial certified product in a year and a half from now. So that means that if you're building your high rises, then you can replace it with a 70% lighter, a fraction of the embodied energy kind of a solution. So 5 years ago, I would have answered this question about bottlenecks and obstructions with only bottlenecks and obstructions. But I feel that there is now a climate of action. There is a climate of change, and also very much from the engineers. There is kind of a move to do things better. So thanks also for that question. That's a good question indeed. There is a question if I could share more pragmatic details about joining those separate floor slabs together to guarantee stiffness in the last building. So yes and no. What I can talk about is a little bit that indeed how we are developing these floors now, they're developed to be in connection with a frame structure. So that the frame of the building can actually take the diaphragm action, so to carry the wind loads to the cores, for example, but also can kind of prevent progressive collapse. So if you take a column out, then we redirect the forces in the frame, and so on and so on. So yes, that is true. More pragmatic details I cannot, because then my industry partners would be very angry at me, because then I would be sharing IP in progress. So unfortunately, I cannot. But it's also not, I can say it's not rocket science. I want to emphasize that actually the things that I'm demonstrating are not crazy, are not new, are not kind of out of nowhere. They are a reintroduction of common sense structural principles and shapes that have been very successful for centuries, until they were all thrown away in the last 150 years. But what I am trying to demonstrate is that today we have different constraints. We have these real climatic pressures. We have the real challenge also we have the real opportunities of computational methods and digital fabrication that can extend the range of feasible opportunities. So I'm sorry that I cannot share more details at this point, but I hope to be able to share it soon indeed. Okay, so open source, that is a very, very important question. Thanks for all these questions. These are fantastic questions indeed. So open sourceness, yes. I mean, in the beginning, it feels a little bit like a weird strategy, because why would you give everything, all your in-house kind of knowledge away? So that is maybe the first notion that you have with open source. The key thing that drives us is basically, we started this framework from our own group, for our own group, but it just grew bigger and bigger and bigger. And the reason that we did this for our own group, and those of you who are in research groups or even in offices, so much knowledge is lost each time a researcher or a really important contributor to your team moves on to a next job or another place, right? And another reality is that each time a new researcher starts, that researcher spends months. In my case, it was even almost a year, because I was by myself doing that topic at MIT. It took me a year to figure out what are the best tools, the best softwares, how to connect all these things to really start to do your research. So you set up your technical kind of framework, pipeline, and so on. And so for those two reasons, we started to develop this platform. That not everyone is redoing the same thing. Like, how silly is it that every single researcher until recently had to waste their time figuring out how to best connect their favorite, whatever you use as a modeling interface, and so on and so on. So now this is given for free. So that means that researchers that start with Compass get the experience of all the other people that use Compass before. But more importantly, what Compass does is that beyond reproducibility of papers, it really makes, in a robust way, your research, your solutions available to others. So that means that you actually get more citations. You get credit for your work. If you don't share your work, there's a lot of smart people in the world. There's a lot of people in the world that are at least as smart as you. And if you don't share your ideas, then someone else will just interpret them and re-implement them and not give you credit. So actually being open source not only allows research to faster grow and to learn from each other, but also to collaborate within very different fields and so on. But it's more importantly, it actually allows you to get more credit for your work, right? And so I think that is an important aspect about open source. By the way, for that question about open source, Compass follows an MIT license. That means that you are also welcome to use all of the information that you will find in the Compass ecosystem, which is growing almost exponentially lately, and to use it also for commercial purposes. So you don't have to share what you are doing with Compass. So that is maybe an interesting kind of thing. Yeah. Yeah, so there's questions about the robustness if pieces come out. So specifically, this question was about the shell in Venice, the stone vault. Indeed, that is something that was requested from us. We were requested from the engineer of record locally in Venice. We were asked, what happens if you take out multiple kind of parts? What happens if you drop a support by multiple centimeters? What happens when there is a seismic kind of thing? And that is actually, all of these can be answered with the same answer that I gave in my very first answer to how, is actually because of the good double curve geometry. If you pinch a little hole, you can find so many different load paths that flow around that hole that basically the shell will be stable. Actually, what you would have is like a dome with an opening in the middle, right? That also works, because it creates these hoop forces in compression around it, and then you have this arch action going to the support. So something similar would happen when you take pieces out. Of course, at a certain point, you cannot take one of the main supports entirely out. That is very clear. So it is also clear that in these funicular kind of systems, particularly if you're pushing them to be fully unreinforced, that you then need to very carefully control the boundary conditions. So and that is where we have the only reinforcement steel left that is actually in the post-tensioning of the boundaries, right? But this is again, I would argue there, nothing comes for free. I mean, the global bending doesn't disappear, but you actually redirect the local bending forces in a combination of pure compression, which offers efficiency in the compression material, and tension in the tension ties. Yeah. Okay, those are the questions on the chat. So maybe there's some more questions on the live stream.
I think they are quite shy. Only
quite shy. Okay. Well, but here on the chat, we're not shy, and they're all extremely good questions also. So thanks a lot for those.
But there are 5,000 audience here.
Oh, wow, great. Thanks everyone for joining. It's a great honor, very exciting. Hope to see you all in person. when I come and visit. Yes.
Yeah, maybe next year when it's more safe.
Yeah, exactly.
Maybe I have another question because at the beginning you already talk about in a global perspective, like the CO2 emission and the pollution. So actually, housing and construction is a critical issue in China here, and sometimes government propose a prefabricated system. So some of your projects, you cast the concrete, spray the concrete on the site, and some of them are using prefabricated components. So what's your opinion about this balance between prefabricated and on-site construction?
So thanks. Actually, a really important question, because I didn't talk about this explicitly, but this question is actually one of the things that keeps us busy most. And I'll first answer it with a very vague kind of global statement, but one that I nonetheless believe is extremely important, is that it really depends. It really depends on the context. It depends also on the situation, on the level of skill available, on the realistic logistics on site. So will you have a crane on site and not, and so on and so on. So that is maybe a first kind of thing that I do believe that, and I want to bring this back to my lecture as well, right? So with my lecture, I don't want to say that the rest of the world needs to do what we do. I just wanted to clarify that I really believe that we need to act, that we need to be more responsible as kind of a design and construction community. And I showed a hint, or in my opinion, one good strategy, but we need many, many strategies, because, for example, the same materials are not sustainable everywhere. Like there's parts in the world where you cannot find any timber closely, where more bamboo and local soils and so on. So then I would do these kind of things. But okay, so to come back to the core of your question, I personally believe a lot in prefabrication, and particularly when you combine this to the concept of design for manufacturing automation. What I mean by that is that the obvious kind of arguments of more precise kind of tolerances are possible. And indeed, if you actually look at many of the building codes, the safety factors also have very much to do with the messiness or the imprecision of materials. So you see that indeed in a concrete construction has much higher safety factors than a steel construction. And this is one-to-one related also with the expected tolerances on site. And so with prefabrication, you can do much better. You can actually be much more precise, but then actually you could really rethink the delivery of a project. And particularly also, and I know that this is already done in a Chinese context often, that the fastest way is just a steel frame structure that goes up, and then you fill it in, and in just like, so maybe some of you are not impressed by the 3.5 months that I was talking about for the crazy shell we did with Zurich Architects, because I know you work in very different contexts. But then, for example, for that steel building, to there be able to provide a much lighter, much more less polluting kind of floor in that steel building that can be clicked in place, to me, that is really the future. Because that means that we can have a faster delivery of projects that at the same time are sustainable. And so that means, in my opinion, win-win, because that also can then be economically argued and become viable towards clients, right? And so I very much believe in prefab for the precision that it offers, so that you can be even more optimal, but more importantly, because of the rethinking of the building process and the sequences and so on and so on. So, and just to share, this floor system that we are developing is indeed a discretized floor, like the one we were testing, out of different pieces, and as a prefab floor as well. Yeah.
Thank you. So one question from audience, he asked, in your video, like some of the projects you still need a lot of labor work.
Yeah.
So do you think about adding automation into the construction process? Like what you imagine what's the future?
Yeah, again, it depends. It depends because it's kind of interesting. So the project in India, we're trying to get all the labor out, and that is because in India they have an entire lack of skilled labor, and everything apparently the labor is very hard at following instructions, right? And this is not my statement, it's the statement of my Indian colleagues. And I kept saying like, no, but you cannot mean what you say, but they kept emphasizing that this is an issue. So in India, we're trying to do a full automation to kind of provide the lowest cost housing. But when we worked together with South Africa, there the requirement, in fact, was to develop systems that activate as much labor as possible. So basically, they want to offer lower skilled people opportunities to work, right? And so that is very different than when we work in Switzerland, where labor costs are gigantically high. There we want to really try to have only precise and punctual kind of input of labor. And that, for example, when you look at the assembly of the concrete shell with this kit of parts that could just be connected on site, so there we just needed, in fact, in the final shell that is now under construction on site, we had just 2 laborers that were there for a week and a half, right? So this them for what they're good for, right? So it would be very hard to program robots to kind of start to connect that cable net, while this could be very straightforwardly be done by humans, right? And so I think it depends. It depends on what tasks and it depends on what contexts. So I think if you can give more interesting roles in certain contexts to humans, or really offer new opportunities for skills and crafts in a developing world context, then I think having labor in there is actually a good idea. Yeah. So again, it depends, but it comes back to your other question about prefabrication. For a Western or a context, there we are indeed developing a system that is lightweight, prefab, and really capitalizes on as much automation as possible, because it is in a context where labor is extremely expensive, and so that doesn't make sense in that. Yeah.
Thank you. Eventually, could you introduce like your team a little bit, like how many people, like the background is architecture, and how many are engineering?
Okay. Yeah, so typically, so there is quite a few on, actually most of the team have, no, that's not true. Let's say that 1/3 of the team have a formal mixed background, like Tom and I, so lead my team with Tom van Melen, who developed also Compass. We really studied both architecture and engineering, right? Either in parallel or in separate kind of stages. So 1/3 of my team is like that, so they come from a mixed background. 1/3 of my team are kind of technically interested, for sure, geometry experts, so architectural geometry expert architects. And then maybe 1/3 of my team are engineers with an interest and an ability or a sensitivity to design, right? But I have to admit that I am starting to more and more increase the proportion of the engineers, because actually it is if you provide them these frameworks, and particularly how we approach our problems, it's easier to find an engineer with all the technical background with the design sensitivity than to find an architect that has sufficient math, structural mechanics, and so on kind of base to really start to push the things that we're doing. And maybe what I'm saying is a little bit unfair, but that has to do with what I said somewhere in the beginning of my talk, is that I am no longer satisfied. I'm in fact frustrated with pavilions, with demonstrators. I mean, we had to do this to actually show that what we do is not entirely theoretical and silly. So we had to go through that stage, but we really want to focus on the much harder next step. Like, how do you really go from a good idea doesn't mean anything if you don't kind of really start to confront it with all the realities and bottlenecks, as one of your colleagues asked earlier, of practice. And so those next steps demand much more sophisticated analysis, inclusion of performance criteria, and so on. So for our group is more migrating a little bit more towards engineering, just because of the ambition to do much more knowledge and technology transfer. And like Professor Hoverstadt, Ludger Hoverstadt, we are hoping to become as a team also kind of a catalyst of startups and spin-offs, in the sense that we actually hope to prepare more and more of our team to actually take their research to that next level. And so for that, you need quite a lot of technical and engineering background and competence as well. And so so we are moving a little bit more towards the engineers. Yeah.
We are looking forward to the next level. Thank you.
Okay.
Thank you very much.
Yeah.
Yes, thank you for the lecture and answer our questions. Yeah.
You're very welcome. Thanks again for the invitation. And thanks everyone for joining. And I look forward to keep this conversation going next time when we see each other, hopefully in Nanjing. Yes.
Yeah.
Perfect.
So
bye then.
have a nice day. Yeah.
Yeah, you too. Thank you. Bye-bye.
See you. Thank you all for coming to this webinar. And today, still at 4 o'clock, we have Professor Li Biao for his session. See you tomorrow.